Hey deep divers, ready for another deep dive? This time we're tackling multi-scale flow problems. Sounds kind of niche, maybe even a bit intimidating. Trust me, it's way cooler than it sounds. So some of you sent over this seriously hardcore research paper, Multicontinuum Splitting Scheme for Multiscale Flow Problems. Definitely looking for some next level insights there. Lucky for you, we've got expert speaker with us today. They eat, sleep, and breathe multi-scale modeling. But before we unleash all the jargon, let's set the scene, all right? Imagine oil flowing underground right through these rock formations. Some rocks, super permeable. Oil just zips through them. Others, not so much, like trying to squeeze honey through a coffee filter. That right there, my friends, is a classic multi-scale problem. Tons of tiny variations, all happening at different scales. Now imagine trying to model that, to actually simulate it accurately. It's got to be a nightmare, huh? Expert speaker.
Oh, absolutely. Traditional methods, they either need these insanely detailed grids, like mapping every single grain of sand. Talk about a computational headache.
You'd need a supercomputer the size of a planet.
Practically. Or the other option, they oversimplify everything, sacrifice accuracy just to make the calculations manageable. Imagine trying to represent a high-res photograph using only like 10 pixels.
You'd lose all the detail, all the nuance.
Exactly. You just end up with a blurry mess. That's where this paper's proposal comes in. The multi-continuum splitting scheme. It's all about finding that sweet spot.
Okay, continuum. There's one of those words that always makes me do a double take. What's it actually mean in this context?
Think of it like this. Instead of modeling every single rock individually, we group similar ones together. These groups. Those are our continua. It's a way to simplify the picture without losing too much detail.
So instead of a million different rocks, we might have, say, 3 continua. High permeability, medium, and low. Something like that.
You got it. Each continuum represents an average behavior. And crucially, we can model them on a much coarser grid. So we're not sacrificing accuracy, but we are making the computations way more manageable.
Clever. So it's all about working smarter, not harder. Finding that balance between accuracy and efficiency.
Exactly. And that's where this whole splitting scheme part comes in. They take it a step further with this concept of partially explicit time discretization.
Okay, now we're getting into the real brain-bending stuff. Should I be taking notes, or is this a hide-under-the-table moment?
No need to panic. It's actually quite elegant when you break it down. It's like this, we've already grouped our rocks, right? Those continue, well, they don't all change at the same rate as the oil flows through. Some, like those high permeability ones, they're practically speed demons. Others, more like slow and steady, wins the race.
So we've got our fast flow continua, our slow flow continua. What's the play?
This splitting scheme, it's clever, right? It calculates each continuum at different time intervals.
Hold on, we don't have to calculate everything at the same rate. That seems way more efficient.
Exactly. It's all about strategy. Those rapidly changing continua, we treat them implicitly. More frequent calculations, got to keep up with all that action. But the slower ones, we can treat those explicitly. Fewer calculations, less computational heavy lifting, and we're not sacrificing accuracy.
So it's like checking your stock portfolio every hour versus watering your plants once a week.
Yeah.
Gotta prioritize.
Now you're getting it. It's all about knowing where to focus that computational microscope.
This is blowing my mind. But how do we even figure out which continuum needs which treatment? Is there like a secret formula or something?
There is. It's called the Rayleigh quotient problem. Yeah, it's a mouthful.
Sounds pretty intense.
Yeah.
Like physics textbook intense.
Well, it's a bit mathy, but I promise it's not as scary as it sounds. Imagine it like this. The Rayleigh quotient, it basically helps us figure out, like, the personality of each continuum, how quickly or slowly it changes. Like, is it a speed demon or a slow poke?
So we're not just lumping them into any old group. We're actually analyzing their behavior, seeing which calculation method fits best.
Yep.
Pretty neat.
Exactly. It's all about finding that perfect match.
But it got me thinking, you know, we've talked a lot about splitting these problems into continua, right? And it seems like finding the absolute optimal way to do that is, like, crucial.
Yeah, it can make all the difference.
What if, and hear me out on this, what if we could take the guesswork out of it completely?
Oh, I like where you're going with this.
What if instead of relying on, you know, human intuition or trial and error, we could use AI? Like, imagine AI that could analyze these multi-scale problems and be like, boom, here's the absolute best way to divide this up into continua.
Wow. That would be a game changer. We're basically talking on automating a key part of this whole process.
Exactly. And think about the possibilities. We could solve even more complex problems way more efficiently. We could uncover hidden relationships that we hadn't even considered before.
It's like giving the AI a superpower. letting it see patterns and connections that would take us, like, years to figure out.
It's incredible to think about what we could achieve with that kind of computational power at our fingertips.
It really highlights how this field is constantly evolving, always pushing the boundaries.
Well, deep divers, we've certainly given you a lot to chew on today. From the nitty-gritty of these multiscale flow problems to the huge impact this research could have. I mean, we're talking everything from designing better materials to, like, understanding climate change. It's mind-blowing. A huge thanks to expert speaker for walking us through all this. I feel like I just got a serious brain workout.
Anytime. Glad to be here.
And to all you deep divers out there, keep those curiosity engines running, and we'll catch you on our next deep dive.
Ever feel like you're waiting forever for your computer to finish something complicated?
Yeah.
Like, imagine it's simulating something super intricate, like oil flowing underground, or the heat spreading through your phone's circuit board.
Yeah, talk about a long wait, that's for sure. And we're not talking a few minutes here. These multiscale flow problems, as they're called, simulating those could take weeks, months, even years to crunch those numbers.
Okay, so time is clearly a factor. But what's so important about these simulations? Why should we care if they take a while?
Because simulating these flows accurately could be huge. I mean, imagine designing lighter materials for airplanes, that are still strong.
Okay, yeah.
That's big for fuel efficiency, less emissions.
Yeah.
Or, picture this, extracting oil and gas with way less environmental impact, just because we can model the subsurface really, really precisely.
Okay, I'm listening. Faster simulations, good for tech, energy, environment. I get it. So what's the holdup? Why are these simulations so slow?
It really comes down to just how complex these flows are. Imagine tracking every single pore in a rock formation, or every tiny variation in, like, the structure of a material.
Yeah.
It's mind-boggling. Traditional methods, they basically try to account for every tiny detail, and that takes a ton of computing power.
Like counting every grain of sand on a beach, right?
Yeah, basically.
It'll take a while. So how does this new research we're looking at tackle this? The paper's called Multicontinuum Splitting Scheme for Multiscale Flow Problems.
Catchy, right.
Definitely rolls right off the tongue.
Well, maybe not the best name, but the idea is really smart. Instead of simulating every microscopic detail, they group similar areas in the material and treat them as one continuum.
Okay, so simplifying things by working with bigger chunks.
Right.
But don't we lose important information that way?
That's the cool part. They realized not all continua are the same. Some parts of a flow, like, say, water squeezing through a narrow pipe, it changes quickly. Others, like water flowing through a wide pipe, much more slowly.
So it's like the difference between a car chase and, like, a relaxed walk in the park. You need more detail for that fast movement.
Yeah, exactly. And just like you wouldn't film those two things at the same speed, this splitting thing uses different treatments for the fast and slow continua.
Okay, what does that mean, to treat them differently?
Think of it like this. For the fast continua, where things are changing fast, they use a really accurate but slower method, like capturing every single frame of that car chase.
Gotcha.
But for the slow continua, they use a faster method that's still good because the changes are smoother.
So they're optimizing for speed and accuracy. Using the right tool for the job, I like it. But this sounds super complex. How do they even know which parts are fast and which are slow?
It's all about analyzing something called contrast. In our example, high contrast is like a big difference in the width between our widest pipe and our narrowest.
So high contrast means bigger, more sudden changes, makes it trickier.
Exactly. And the really cool thing is the splitting method, it's almost immune to those problems caused by high contrast.
Oh, wow.
They've even found a way to figure out the absolute best way to divide those continua to get the best speed and accuracy.
Hold on, so they're not just simplifying, they're finding the best way to simplify. That's incredible. How?
Well, it's a technique similar to how engineers find the strongest parts of a structure, but instead of stress, they're analyzing the mathematical properties of the simulation.
Okay.
It's pretty high level. But basically, they found a way to pinpoint the optimal way to break down the problem.
Wow, that's really impressive. So we've talked about the how a bit, but let's get back to the why. What does this mean practically? Real-world impact.
Oh, tons of potential applications. Start with something I know you're into. Clean energy.
Yeah.
This research could change the game for making better solar cells. Imagine being able to capture way more of the solar spectrum. That means cheaper, more efficient solar energy.
Now you're speaking my language. Affordable, sustainable energy. That's what we need. What else?
How about this? Remember those lightweight, super strong materials?
Yeah.
Imagine using those to build electric cars with crazy good range.
Yeah.
And because we're using less material, they're more affordable. We're talking electric vehicles for everyone.
Okay, that's huge. Making EVs actually practical and affordable, that's a big deal for fighting climate change. What other fields are we talking about?
Well, drug discovery is a big one. Imagine simulating how different drug compounds interact with the body at a molecular level.
Okay.
We could develop more effective meds with fewer side effects, and it could really speed up the whole drug discovery process.
Wow, this is amazing. We could revolutionize so many industries.
And we're really just getting started. This research opens so many doors. But before we get too carried away, let's get back to the specifics of this multi-continuum splitting scheme.
Okay.
I think it's worth digging a little deeper into how they differentiate those fast and slow continua.
You're right. Let's unpack that. Understanding that seems pretty important. What makes a continuum fast or slow?
Okay, so imagine you've got water flowing through all these different pipes. Some pipes are wide, the water flows through them pretty slowly. Others are super narrow, the water has to squeeze through a lot faster.
Okay, so the fast continua are like the narrow pipes and the slow ones are the wider ones.
Exactly. But instead of just water, we're talking about, oil, gas, heat, even electrical currents. And those pipes could be anything from the pores in rock to like the pathways in a computer chip.
So the fast ones are where the flow is more restricted, more dynamic, needs more detailed simulation.
Exactly. It's like the fast continua are where the action is, where things are changing really fast over very small distances. To capture that accurately, you need to take very small steps in the simulation, which computationally, that gets expensive.
Okay, that makes sense. More detail, more calculations, more time. What about those slow continuas? Like you said, wider pipes, more leisurely flow?
Exactly. In these areas, the flow changes more gradually over larger distances. We can take bigger steps in the simulation without losing too much accuracy. It's all about efficiency.
Okay, so we've defined our fast and slow continua. Now, how does this scheme actually tell them apart in the simulation? How does it know when to use the high-speed camera versus the leisurely stroll approach?
That's where the magic of math comes in. They use a combination of techniques to treat these different continuas differently. For the fast ones, they use a method called implicit treatment.
Implicit treatment, that sounds familiar. That's the more accurate but slower approach, right?
You got it. With implicit treatment, the simulation has to solve a complicated equation at each time step to figure out the flow properties. It's like taking a really detailed snapshot of the flow at every single moment.
I see why that would be computationally intensive, but also necessary for those rapidly changing areas. What about the slow continua? How do those work?
For the slow continua, they use something called explicit treatment. It's much faster because it doesn't have to solve that complicated equation at every single time step. Instead, it uses information from the previous time step to estimate the flow at the current one.
So like a shortcut. But it's still accurate enough because the flow isn't changing as much in those areas.
Exactly. Finding the right balance between accuracy and efficiency is key. And by combining implicit treatment for the fast parts and explicit treatment for the slow parts, this splitting scheme really optimizes both.
Brilliant. So they've taken this crazy complex problem and broken it down into manageable pieces and then found the most efficient way to tackle each one.
It's elegant, really. And the results are impressive. But before we get into those, I think we should take a closer look at the math behind this whole multi-continuum splitting scheme.
Okay, let's do it. Now, don't get too technical on me, but how do they actually implement this splitting so that a computer can understand it?
At the heart of it all is this technique called, are you ready for it? Multi-continuum homogenization.
Multi-continuum homogenization. Yeah, I think I'm going to need you to break that one down for me.
It's not as intimidating as it sounds. It's basically a way to represent the overall flow behavior of the material using like a set of simplified equations.
Yeah.
Think of it like a compressed version of the full, super detailed ones, but it still captures the essential physics at different scales.
So they're creating a sort of averaged out version of the flow, but one that still accounts for the differences between those fast and slow continua.
Precisely. And those simplified equations are way easier for computers to solve. Think of it like navigating a city with a detailed street map versus a subway map. The subway map just highlights the main routes, the connections that matter most.
Love that analogy. And that streamlined model, is that what lets them speed up the simulations without losing accuracy?
You got it. It's about simplifying things in a smart way.
This is amazing stuff. I can already see how this could revolutionize so many things. Designing new materials, understanding the Earth's climate, the possibilities seem endless.
They really do. But it's important to remember that this is still a pretty new approach. There's a lot more to learn and understand about this method.
Like, for example, how do you choose the right continua for a simulation? Is there a balance between having too few, which might oversimplify things, and too many, which could make the simulation too complex?
That's a great question, and researchers are still working on that. The folks in this paper, they focused on simpler examples to demonstrate how their method works. But in the real world, choosing the right continua is going to be critical. It'll take a lot of expertise and probably some trial and error too.
Sounds like there's still a lot of room for innovation here, which is actually pretty exciting. What are some areas you're most interested in seeing explored further?
Well, one thing that comes to mind is developing adaptive algorithms, ones that can automatically adjust the number and type of continua as the simulation goes on.
So like a self-tuning engine for simulations that constantly optimizes itself for better performance.
Exactly. Imagine a simulation that starts with a simple representation of the flow and then adds detail where it's needed as it goes along.
That would be amazing. You'd get even bigger efficiency gains without sacrificing accuracy where it matters most. What other advancements are you excited about?
I'm really interested in how this method can be used for even more complex problems, like ones that involve fluid flow, heat transfer, and chemical reactions all happening at the same time. We call these multi-physics problems.
Okay, now we're really getting into it. What would a multi-physics problem look like?
Picture this simulating the flow of oil and gas through rock, but you're also accounting for the heat generated during extraction and any chemical reactions going on between all those different components.
Wow, okay. That's a lot of moving parts. So you're not just modeling the flow, you're factoring in temperature changes, chemical interactions, how it all affects each other.
Exactly. Multi-physics problems are incredibly complex, but they're also essential for understanding so many things in the real world.
And this multi-continuum splitting scheme, this could be a key to unlocking that complexity.
It really could. If it lets us simulate these systems more efficiently, it could lead to breakthroughs in enhanced oil recovery, carbon capture and storage, even developing new materials.
This is really groundbreaking stuff. I'm starting to see how this could change how we approach simulations in so many different fields, from material design to climate prediction.
It really could. But it's important to keep in mind, this is still a new approach. There's still a lot we need to learn.
For instance, how does the specific choice of continua impact how accurate and efficient the simulations are? Is there a sweet spot between simplifying things too much and making things too complex?
That's what researchers are trying to figure out. This paper, they look at some simpler examples to show the basics of the method. But in the real world, choosing those continua is going to be really important. It's going to require a good understanding of the physics involved, the math behind it, and some trial and error.
That's so cool. There's still so much room for innovation and improvement. What other areas do you see as being ripe for further exploration?
One thing I'm really interested in is developing algorithms that can automatically adjust the number and types of continua as the simulation progresses.
So like the simulation could start with a pretty basic representation of the flow, and then it would get more complex in areas where more detail is needed.
Exactly. It would be like having a self-tuning engine that constantly optimizes itself for the best performance.
That would be incredible. You could get some huge efficiency gains without having to sacrifice accuracy in the critical areas.
Right.
What other kinds of advancements are you hoping to see in this field?
Well, one area that I'm particularly excited about is seeing how this method can be used for even more complex multi-physics problems. These are problems that involve things like fluid flow, heat transfer, and chemical reactions all happening together.
Wow, that sounds incredibly complex. Can you give me an example of what a multiphysics problem might look like?
Sure. Imagine you're trying to simulate the flow of oil and gas through a porous rock formation. But you also have to take into account the heat that's generated during the extraction process and any chemical reactions that are happening between the different components.
Okay, yeah, that's a lot to consider. So you're not just modeling the flow, you're also factoring in things like temperature changes, chemical reactions, and how those things all influence each other.
Exactly. These multi-physics problems are incredibly complex, but they're also crucial for understanding a lot of real-world phenomena.
And this multi-continuum splitting scheme could be the key to making those simulations more manageable.
It really could. It has the potential to be a game changer. By letting us simulate those complex systems more efficiently, it could lead to breakthroughs in things like more efficient oil recovery, carbon capture and storage, and even in developing completely new materials.
This is seriously impressive stuff. I can't wait to see where this research goes next.
Me neither. It's an incredible time to be working in this field.
Yeah.
I think we're just starting to scratch the surface of what's possible.
I completely agree. And to our listeners, thanks for joining us on this deep dive into the world of multi-scale flow simulations.
It's been a pleasure.
We've covered a lot of ground today, from the nitty-gritty of how this technology actually works to its potential to revolutionize entire industries and tackle global challenges.
And as we move into this future filled with possibilities, it's more important than ever to think about the ethical implications of this technology.
Exactly. No technology is perfect, and as these simulations become even more powerful and more central to our decision-making, we need to be really thoughtful about how we use them.
I couldn't agree more.
You know, it's really got me thinking about how this research could totally change how we design things.
Oh, for sure. This isn't just about making simulations faster. It's about having a whole new level of control over the materials we use every day.
Like, imagine lighter, stronger, more sustainable materials thanks to these simulations.
Exactly. Imagine a car frame that's like half the weight but twice as strong. You'd use less material, so big fuel savings, lower emissions. It's amazing.
Now, that's a win-win. Less material, fewer emissions. What other cool applications can we think of when it comes to materials?
Well, take solar cells.
Yeah.
What if we could design them to capture way more of the sun's energy? Cheaper, more efficient solar power for everyone.
Okay, now that's something I'm really interested in. Affordable and efficient solar, everyone wants that. But let's shift gears a bit. Energy exploration. How could this tech change things there?
Oh, the oil and gas industry. They could use this in a big way. Getting oil and gas out of the ground, it's tough, it's imprecise. But imagine having this detailed, like, virtual map of what's underground. You'd know exactly where to drill.
That's huge. More efficient, lower cost, less environmental impact because you're not drilling as much.
Exactly. It's all about getting those resources in a smarter way. Less waste, lower risk of spills, all that. And it's not just fossil fuels either. This could change how we get geothermal energy too.
Geothermal, you mean using the Earth's heat as energy? That's always seemed so cool, but I bet it's super complicated.
It is. To do it right, you really need to understand the Earth's thermal processes, what's going on under the surface.
And that's where these simulations come in, giving us a better picture.
Exactly. We can pinpoint the best spots for geothermal plants, make them as efficient as possible, even predict and avoid problems like induced seismicity.
Induced seismicity, like those little earthquakes that can happen with geothermal. So it's about using this powerful energy, but doing it safely.
Exactly. And that just shows how versatile this technology is. It can make fossil fuels better, and it can boost renewables too.
That's what's so interesting about all this. It can have a positive impact in so many different areas. But before we move on, I want to touch on one more area where I think these simulations could be really important: climate modeling.
Oh, absolutely. Climate modeling, that's a tough one. So complex, but so important. And yeah, this tech could really change the game there.
Climate science, it's all about understanding these incredibly complex systems. How can this new simulation method help us with all that?
Imagine creating these climate models that are so much more detailed, so much more accurate than anything we have now. You could factor in everything. I'm talking ocean currents, clouds, aerosols, the whole 9 yards.
So instead of just predicting these broad climate trends, we could start to model specific events like extreme weather or regional changes with way more accuracy.
Exactly. We could look at all kinds of different climate scenarios, test different solutions, and ultimately make better decisions about how to tackle climate change.
Now that's putting knowledge into action. It's not just about understanding these systems, it's about using that understanding to actually do something.
Right. And that's what makes this research so exciting to me. It's not just theoretical. It's about solving problems, making the world better.
Exactly. It's like we're giving humanity this powerful new tool, a new way to see and interact with the world.
Exactly. But like any powerful tool, we have to use it responsibly. We have to think about the ethics.
I completely agree. And that's a perfect segue into our next discussion. Let's talk about some of those ethical considerations, because with great power comes great responsibility. We're back for the final part of our deep dive. We covered some really incredible stuff about these multi-scale flow simulations.
It's been pretty mind-blowing, right? From designing lighter cars to developing more effective drugs, even modeling the Earth's climate. The possibilities seem endless.
They really do. But it's important to remember that
every technology comes with its own set of challenges.
Absolutely. As these simulations become more powerful and more integrated into our decision-making, we really need to consider the ethical implications.
It's like having this key that can unlock so much potential, but we have to make sure we're using it wisely. What are some of the things we need to be thinking about as this technology keeps advancing?
I think one of the most crucial things is making sure that these simulations are used for the right reasons, for the benefit of humanity and the planet.
That seems obvious, but how do we actually ensure that happens?
It's about building a sense of responsibility, within the scientific and engineering communities. We need people who aren't just brilliant technically, but also ethically aware. People who are asking not just, can we do this, but should we do this?
So it's about making sure these tools are used to create a better future for everyone.
Exactly. And that also means being aware of potential biases that could creep into these simulations.
You mentioned that earlier. Could you elaborate on that a bit? How could bias become a problem here?
Well, think about it. These simulations, they rely on massive amounts of data to make predictions, to generate designs. If that data is incomplete or biased in some way, the simulations could actually make those biases worse.
So, for example, if a simulation is being used to design a bridge, but the data it's trained on is only from bridges in a certain area or climate, it might not work so well in other places.
Exactly. Or imagine a simulation for developing new medicines. If the data isn't representative of diverse populations, the treatments that are developed might not be equally effective for everyone.
That's a really important point. So transparency is key here. We need to be able to understand how these simulations work, what data they're using, and what assumptions are built into them.
I totally agree. Transparency builds trust, and it lets more people weigh in and make sure things are being done right.
And it's not just about transparency within the scientific community. It's also about collaborating and sharing knowledge across different fields and with people all over the world. We need ethicists, social scientists, policymakers, everyone working together to make sure this technology is used responsibly.
Absolutely. This isn't just a technical challenge, it's a societal one. We need to be having open conversations about the potential benefits and risks of this technology. We need to work together to make sure it's used for good.
And speaking of the future, what are you most excited about when it comes to multi-scale flow simulations? What breakthroughs are you most eager to see?
One area that I'm really fascinated by is the potential to use these simulations to understand complex biological systems. Like imagine being able to model the human brain or track how diseases spread through a population with incredible accuracy.
Those are some ambitious goals, but they don't seem totally impossible with all the advancements we're seeing. What about you? What has you most excited in this field?
I'm really excited about the potential for clean energy. Imagine designing incredibly efficient solar panels or optimizing wind farms to harness renewable energy like never before. That's a game changer.
It's incredible how this technology can be applied to things at such different scales, from designing materials at the atomic level to modeling global climate systems.
It really shows how interconnected everything is, and it highlights how important it is to collaborate across disciplines to bring different perspectives to the table.
I completely agree. We need to break down those barriers between different fields, talk to each other, work together, and approach these challenges with a shared sense of purpose. Exactly. We're all in this together. Scientists, engineers, policymakers, and everyday citizens. If we can harness the power of these incredible technologies thoughtfully and collaboratively, we can build a brighter and more sustainable future for everyone.
Well said. I, for one, am really excited to be a part of it.
Me too. And to our listeners, thank you so much for joining us on this incredible journey. We hope this deep dive has sparked your curiosity and left you with a sense of wonder about the amazing potential of this technology and the responsibility we all share in shaping its future.
Ever try picturing, oil flowing through those tiny little pores in underground rock?
It's a weird thing to think about.
Or how about heat spreading through, a material that's made up of completely different stuff?
Yeah.
These are what we call multiscale flow problems. Things behaving differently on a tiny level compared to the whole system, right? And that's what we're diving into today.
That's right.
With this paper that's promising to make solving these crazy complex equations way faster.
You're right. It's a challenge that, it pops up everywhere. Science, engineering, you name it. And the traditional ways of solving them, they just haven't been able to keep up.
And this is where this new research comes in, right? Because we can solve these problems faster. We're talking huge implications.
Yeah.
Designing better batteries, more accurate weather forecasts.
Oh, absolutely.
Maybe even understanding how diseases spread.
Huge, yeah. And what I think is really interesting is this paper, they use really concrete examples to explain these, kind of tricky mathematical concepts, just like the ones you were talking about. They illustrate like what we call multiscale and high contrast problems.
Okay, so walk me through it. What makes these problems so hard to solve in the first place?
Well, picture this. You're trying to figure out a traffic jam, right? But you have to look at every single car's movement, and at the same time, you're zoomed out looking at the whole city map.
Oof, that's a lot to keep track of.
Right. And traditional methods, they use this super fine mesh, like a grid of tiny squares, to try and capture all the little variations happening at these different scales.
It's like trying to paint a detailed portrait, but only using grains of sand. Technically possible, but...
Exactly. Incredibly tedious and computationally expensive. And to make matters worse, there's this thing called the time step issue.
Time step issue, okay.
To keep the calculations stable, you often need to use really, really small steps in time, which just piles onto the computational cost. It's like, imagine walking across this rocky terrain, huge differences in elevation. You're forced to take these tiny, careful steps, really slows you down.
Okay, so we've got these crazy complex problems. They take forever to solve, need a ton of computing power. So what's the solution? What do they propose in the paper?
Well, they build on this really clever approach called, get ready for it, multi-continuum homogenization.
Okay, before you scare everyone away with the jargon.
Right. I know it sounds intimidating, but stay with me.
Okay.
It's actually quite elegant when you get down to it. So instead of trying to find one solution for the entire problem, imagine dividing it up into these different continua. Think of these as regions, each with their own distinct properties, like different neighborhoods in our city traffic analogy.
So we're breaking down a complex recipe into more manageable steps, like focusing on the batter, then the frosting, then the filling separately, instead of trying to bake this whole cake all at once.
Exactly. And to capture what's going on within each of these continuas, we use what are called basis functions. So imagine each continuum as a puzzle piece. Solving these cell problems, it's like finding the right shape and pattern for each piece so that they all fit together to form the complete picture of our flow problem.
Is it like that, the puzzle piece analogy?
And the beauty of this is that it lets us use what we call a coarser mesh. Instead of those tiny little squares, we can use bigger ones, and that makes the computations way faster.
So we're simplifying the problem without losing too much detail.
You got it. But it gets even more interesting. What this paper does is they introduce this new method called multi-continuum splitting schemes. And instead of treating all the continuum the same, they split them into two groups based on how fast or slow things are changing within them.
So they're, optimizing the optimization? Some next level problem solving there.
Yeah.
Tell me more.
Yeah, it's a really neat strategy. They recognize that some of these groups, these fast ones, and they often correspond to areas with high permeability in, like our oil flow example, they need more computational muscle, let's say, and they should be treated differently. We call this treating them implicitly, and it's kind of like tackling a task that needs your full attention right now.
Okay, so then there's the slow groups. They get treated differently.
You got it. These slow groups where things are changing more gradually, those can be treated what we call explicitly. Less computationally intense, like scheduling a task for later, important, but not urgent. And that's a big part of how they speed things up.
Now, I got to ask, and I'm sure our listeners are wondering the same thing.
Right.
Will it blend? I mean, will these calculations stay stable? Because no one wants their simulation to go haywire.
Right. That's what's so cool about this paper. They don't shy away from that stability question at all.
Okay, good.
And what they find is actually pretty amazing. The stability of these schemes, it doesn't actually depend on the contrast, meaning that difference between the highest and lowest values in our problem.
So no matter how rocky that terrain is, we can still, stride across it. We don't have to tiptoe.
Exactly. No more tiptoeing, which is a huge deal, especially for those problems with really stark contrast like we were talking about.
Right, okay.
And it gets even better. They actually show that this holds true even for more complex cases, as long as you choose the continuum well. It's really quite robust.
Yeah. Okay, so they've found a method that's fast and it's reliable. But they don't stop there, do they?
Yeah.
They actually try to find the absolute best way to split those continua in the first place, right?
You're reading my mind. That's exactly it. They ask, can we actually optimize the split itself? Can we get even more efficient? And that's where things get,
even more mathematically interesting.
Okay, so break it down for me. How do they even go about doing that?
Well, they basically formulate it as this very special kind of mathematical problem, a way to figure out the best way to divide and conquer, if you will.
Divide and conquer, I like it.
Right. So when we're talking about finding the absolute best way to split something mathematically, we often use what's called an eigenvalue problem.
Eigenvalue problem. Okay.
Yeah. So think about it this way. You've got a guitar string,
Yeah.
right?
All right.
When you pluck it, it's going to vibrate at a certain frequency, makes a particular note, right?
Right.
That frequency. That's kind of like an eigenvalue. And the actual way that the string vibrates, that shape, that's like an eigenvector.
Okay, I think I'm starting to get it.
So in our case, instead of guitar string, we've got our multiscale flow problem. And we're trying to find the best vibration, so to speak, the optimal split that gives us the most efficient solution.
So they're finding like the sweet spot for splitting the problem to get the fastest, most accurate results.
You got it. It's like they're taking this really complex task and turning it into something we know how to solve, this eigenvalue problem. That lets them pinpoint the absolute best split for maximum efficiency.
That's pretty impressive. But of course, it all comes down to whether this actually works in the real world, right?
Mm-hmm.
Like, did they actually test it out?
Oh, absolutely they did. They applied it to a whole bunch of different examples. And the results, really impressive. Not only was their approach accurate, it was way faster than traditional methods, especially for those tricky high contrast problems.
So it's safe to say they found like a shortcut for solving these super complex equations.
In a way, yeah, you could say that. But, it's not just about speed, right?
Right.
What I think is so remarkable is how this method tackles a problem that's been bugging researchers forever. Finding a way to solve these multi-scale problems efficiently without sacrificing accuracy. That's huge.
It really is. It's like we're not just solving equations here. We're getting a much deeper understanding of how things work at their core.
Exactly. That's the real power of this research, pushing the boundaries of not just how fast we can compute things, but how we approach these complex problems in all kinds of different areas.
So what's the biggest takeaway for you from all of this? Why should our listener care about any of this?
Honestly, it's the potential of the splitting concept that really gets me excited, like realizing that different parts of a problem change at different speeds, and we can use that to our advantage. This whole idea of identifying what's fast and what's slow in a system,
Yeah.
I think it has the potential to totally change how we approach these really complex problems, not just in physics or engineering, but in things like economics, climate modeling, even how we look at social networks.
It's like this paper has opened up this whole new world of possibilities for understanding really any complex problem.
Yeah. Like, imagine if we could just pinpoint those fast and slow parts of anything. The possibilities are huge.
It's pretty amazing when you think about it. So to our listeners out there, we leave you with this. What multi-scale problem are you facing?
Right. What challenges in your work, your life, I don't know, could benefit from this whole splitting by speed idea?
It's something to think about as you're going about your day, navigating the complexities of the world. Who knows, you might just stumble onto the next big breakthrough.
And when you do, we'll be here ready to dive in and explore it with you.
That's all the time we have for today's deep dive. We hope you found it insightful, maybe even a little bit inspiring.
Until next time, keep those brains engaged. And remember, even the most complex problems, we can break them down, we can understand them.
And sometimes the most elegant solutions come from just looking at things a little differently.
Hey everyone, welcome back. Today we're doing a deep dive into multiscale flow problems.
Multiscale flow problems.
Yeah, and I know it sounds a little intimidating, right? But stick with us because this is really fascinating stuff.
It really is.
Okay, so imagine this. You need to model something like oil flowing through porous rock.
Okay.
You've got these tiny little pores, we're talking almost microscopic, and then you've got this massive, huge scale of the entire oil reservoir.
Right.
That's a massive difference in scale.
It is, and that's exactly what makes these multi-scale problems such a challenge, Traditional methods, they just weren't built to handle these huge discrepancies in scale.
Yeah, it's like you're trying to study the Amazon rainforest, right?
Sure.
And you're trying to analyze every single leaf.
Every single leaf.
But at the same time, you also need to understand the entire ecosystem.
Exactly.
It's a lot to handle.
Yeah, and to add even another layer of complexity, these flow problems often involve what we call parabolic equations.
Parabolic equations.
Yeah, so these equations basically describe how things change, not just in space, but also over time. And that just ramps up the computational difficulty.
Okay, so we've got these huge scale differences, and on top of that, we have these really complex equations that we need to use. So what's the main problem with traditional approaches in this situation? What's the roadblock?
Well, think of it this way. If you want to capture all those tiny details, those microscopic pores in the rock, you would need a superfine mesh in your simulation.
Okay.
It's almost like trying to look at a giant painting with a microscope. You can see every brushstroke, but it takes forever to see the whole thing.
Makes sense.
And here's the catch. Because we are also dealing with time evolution, those parabolic equations to make sure they stay stable, we need to take very small steps in time, especially when we are dealing with very different material properties, like in the oil reservoir example.
So it's like you're stuck.
Kind of, yeah.
You need the superfine mesh for accuracy, but then you need these tiny time steps to make sure everything's stable. No wonder those traditional methods, they hit a wall.
They do. They hit a wall.
But that's where this multi-continuum splitting scheme comes in, right?
Yes, exactly.
The research that you sent me goes into this new approach. I got to be honest with you. The name alone, multi-continuum splitting scheme.
A mouthful.
Yeah, it makes my brain hurt a little bit.
It sounds a lot scarier than it actually is.
Okay.
To understand this new method, we really have to kind of unpack this idea of multi-continuum homogenization first. It's a pretty neat concept.
All right, so hit me with it.
Okay.
Hey, go easy on me with the technical stuff.
Okay, so imagine you're putting together a giant jigsaw puzzle.
Okay.
But instead of focusing on each individual piece, you could group similar pieces together. Like all the blue sky pieces, you make them into bigger chunks.
Okay, so instead of looking at each piece by itself, we're grouping things together based on, like, similarities.
You got it. And those chunks, those are what we call continua. So in this oil reservoir example, you could group similar rock formations.
Okay.
Each continuum then represents a kind of average of all the properties in that region.
So rather than modeling every single grain of sand, we're saying, hey, this whole area is mostly sandstone. Let's just treat it as one thing.
Exactly.
I mean, that makes sense, but doesn't that kind of create inaccuracies, especially at the boundaries between these chunks? Like when the sandstone meets a totally different kind of rock?
That's a great point, and this is where oversampling comes in. Think of it as adding in extra detail at the edges of those puzzle pieces, just to make sure they all fit together really nicely.
I see.
It's a way for us to account for the interactions happening at these boundaries.
Okay, so we are simplifying the problem, but we're doing it in a smart way. We're still trying to capture those really important interactions. Okay, so this is making a lot more sense to me now. But I am still a little bit unclear on where the whole splitting part comes in. That's the part that really makes this new scheme faster, right? Okay, so we're grouping similar parts of the problem together. We're smoothing out the boundaries between them. That's pretty clever. But how does this splitting actually work? And how does it actually make these crazy calculations faster?
So that's where the real magic happens with this method. Instead of tackling the entire problem with the same level of detail, this multi-continuum splitting scheme, it divides it into two parts.
Okay.
One part needs those super precise calculations, the kind that need the fine mesh and the tiny time steps.
Right.
We call this the implicit part.
Okay.
But, and here's the kicker, the other part can actually be approximated without sacrificing the overall accuracy of the solution.
Interesting.
And we call that part the explicit part.
Okay, so it's like when you're reading a really long research paper.
Okay.
Yeah. You know, you pay really close attention to the findings, the methodology, all the really important stuff.
Right.
That's like your implicit part.
Exactly.
But then you might just kind of skim over the literature review. You know, you're not going to read every single word.
Right.
That's your explicit part. You still get the gist of it. You're not really losing any important information.
Exactly. You don't need to sweat every little detail.
Right.
And this clever splitting of the problem, that's what makes the multi-continuum splitting scheme so efficient. Especially for those high-contrast multi-scale problems we talked about, the ones that really make computers sweat.
Yeah, no kidding. This all sounds amazing, but is it reliable? I mean, you're splitting a complex problem in two. Doesn't that risk introducing errors? Or like making the whole simulation unstable?
It's a crucial question.
Yeah.
And you're right to be a little bit cautious.
Yeah.
But the good news is the researchers actually mathematically proved that this scheme is stable.
Okay.
Meaning it can handle slight variations in the problem without going completely off the rails.
So no sudden implosions in our simulated oil reservoir.
No, you're safe, no implosions.
Okay, good.
And what's even more impressive is that this method is what we call contrast independent. Remember how we talked about those extreme differences in properties?
Yeah.
Like the permeability of different rock types?
Yeah.
This scheme doesn't even flinch no matter how big those contrasts are.
Yeah.
That's a big deal in computational science because we need methods that can handle the real world with all its messy variations.
Absolutely. So this method isn't phased by even the most extreme cases.
Exactly.
That's pretty wild. Okay, so how do we actually apply this splitting in a way that works? We can't just randomly divide the problem in two and hope for the best, right?
You're absolutely right. It's not random at all. This is where the researchers got really smart. They had to figure out how to optimize that split because not just any split will do. They needed to find the one that maximizes efficiency without losing accuracy.
Okay, now you're going to have to elaborate on that a little bit. What does optimizing the split actually involve?
So to find the best way to split the problem, they used a tool called an eigenvalue problem.
Okay, eigenvalue problem, yeah. Sounds familiar. I'm having flashbacks to college linear algebra, which I may or may not have slept through.
Yes.
Can you break it down for me? Why is that important here?
Of course. So essentially, an eigenvalue problem is a way to find what we call the most influential or dominant features of a system. Think of it like finding the pressure points, the parts that have the biggest impact on how the whole system behaves.
Got it. So it's like identifying the bottlenecks, the parts that are really slowing down the calculation.
Yes, exactly. And by focusing on those areas with the more accurate implicit calculations, they were able to make the entire scheme way faster.
That's some really clever optimization. So it's not just about splitting the problem, it's about splitting it strategically, like a surgeon making a really precise incision.
Precisely.
This all sounds really fantastic in theory, but did they actually put the scheme to the test, like in a real-world scenario?
They did, yeah. They tested it out on a variety of different scenarios, including a simplified layered field,
Okay.
kind of like our oil reservoir example.
Okay.
But to make things even more interesting, they didn't just stop there. They also tested it on a much more complex, what we call non-periodic case.
Okay, so like a more realistic, kind of messy geological formation.
Exactly.
Cool.
They wanted to see if this multi-continuum splitting scheme, if it could really handle the complexities of a real-world scenario.
And what happened? Did it work?
It did. And the results were really, really exciting. In every single test case, this new method, it produced accurate results, and it did it much faster than any of the traditional approaches. We're talking about a potential game changer here.
This is what gets me excited, right? All right, we went from this kind of theoretical idea of splitting a problem to an actual method that works.
I know. It's really cool.
And it works well.
Yeah.
But I always have to ask, what's the so what? Why should we care about making these simulations faster? How does this impact, you and me in everyday life?
That's the million-dollar question. The potential applications here are huge. I mean, faster simulations mean we can start tackling even more complex problems in a fraction of the time and using less computing power. I mean, think about it. We could have more efficient oil and gas extraction, better groundwater management. We could even use it to understand how blood flows through our cardiovascular system.
Okay, now you're speaking my language. So we're talking about potentially huge breakthroughs in a whole bunch of different fields.
Absolutely. And this is about way more than just crunching numbers faster. It's about pushing the boundaries of what we can even model and understand about the world around us.
Which leads me to my favorite question, the what-if question.
All right, hit me with it.
We've seen how this method works really well for oil reservoir, complex geological formations. But what if we could push it even further? What if we use this multi-continuum splitting scheme to model like really complex systems, things we haven't even thought of yet?
Ooh, that's a good one. That's exactly what researchers are starting to explore right now. Imagine using this approach to model, I don't know, something like climate change on a global scale.
Wow.
Or predicting traffic patterns in a huge city.
Yeah.
Or even, and this is where it gets really interesting, what if we could simulate the behavior of entire economies?
Now, those are some complex systems.
Right.
But the possibilities, it's mind-blowing. If it can handle something as intricate as porous rock, who knows what else we can use it for?
It's true. And that's what's so exciting about science. It's a never-ending journey of discovery. What seems impossible today could be completely normal in the future.
I'm definitely going to be keeping my eye on the multi-continuum splitting scheme. Who knows? Maybe it'll be the next big thing in computational science.
It just might be.
It's already blown my mind, and believe me, I've seen my fair share of complex equations.
Me too. It's a really exciting development, and it has the potential to revolutionize a lot of different fields.
Yeah.
It really shows you what we can accomplish with a little ingenuity and a lot of curiosity.
Well said. All right, everyone, that was our deep dive into the world of multiscale flow problems and this incredible new method, the multi-continuum splitting scheme.
It's a mouthful.
It is, but hopefully you stuck with us. And remember, it's not just about the equations, it's about asking why and so what.
Exactly.
And in this case, the potential is huge.
Huge.
Until next time, stay curious, keep those questions coming.
We'll be here to dive right in.
Right here on The Deep Dive.
Ever stop to think about, like how water seeps through the ground?
Mm-hmm.
Or like when they talk about oil flowing through porous rock.
Mm-hmm. Mm-hmm.
It sounds kind of simple when you say it like that,
Yeah.
but it turns out those processes, they actually happen on all these different scales, right?
Mm.
And getting those tiny details right, those little details, can totally change how we understand things like resource extraction,
Right.
material design. It's a big deal.
Yeah.
So that's what we're diving into today with this research paper on multiscale flow problems.
Yeah, what's really cool about these problems is that even the tiniest little variations in a material, like how the microscopic pores are arranged in a rock, it can totally change how things flow through the whole thing, like on a much larger scale.
It's like those ripple effects.
Exactly.
You know, when you get that like one tiny pebble in a pond,
Sure.
and then suddenly you've got these expanding rings that go way beyond just where the pebble hit.
Perfect analogy. And just like those ripples, the problem with figuring these multi-scale problems out is that, like, the traditional ways we use to model them, they struggle to capture all those crazy details without just, like, drowning in a sea of math.
Yeah, because you'd have to analyze like every single molecule's movement
That's exactly it.
instead of just looking at the overall flow.
You got it. And to do that, you'd need supercomputers and, like, way more time than anyone has to get an accurate simulation.
Right. Okay. So then this paper we're looking at, they are proposing like a shortcut.
Yeah, you could say that. They call it multi-continuum homogenization. So instead of getting lost in every single microscopic detail, we simplify things a bit. We group similar parts of the material together based on how they behave on average.
Okay, so let's unpack this multi-continuum homogenization thing a little bit because it sounds pretty technical.
Sure.
And I'm all for simplifying, but I want to make sure I'm following along.
Absolutely. So imagine like a sponge, right?
Okay, I like sponges.
Instead of like trying to model how the water flows through every single little pore in the sponge, we can group similar pores together. We call these groups continua.
Continua.
Each one represents a bunch of pores that all have similar properties, like maybe their size or how easily water can flow through them, that sort of thing.
So we're basically like creating a simpler version of the sponge, but one that still has the important stuff that affects how the water flows through it.
Exactly, you got it. And the cool thing is, this lets us make these like upscaled equations that describe how the flow behaves on average within each of those continua. So no more supercomputer to simulate every single pore. We can use the simplified model and it's way faster.
That's wild. It's like finding a shortcut that actually gets you to the same place.
I like that, yeah.
But hold on, this paper, that didn't stop there, right? They take this whole simplifying thing even further, right?
You're right. Yeah.
With a technique they call splitting. What is that all about?
All right, so let's stick with your shortcut analogy for a sec. Imagine you're driving somewhere. You have two choices. One's like a scenic route, all winding roads, traffic lights, the whole bit.
Oh, I hate that.
Right. And then the other option is like a highway. Faster, you know what to expect.
Yeah, sign me up for the highway. Always. Efficiency is key.
Exactly. And that's kind of what they are doing here, but with multi-scale flow.
Okay, walk me through it. How does driving relate to, microscopic pores?
So the splitting technique basically takes the problem and divides it up. It looks at how much each part is affected by those tiny variations we were talking about before, the stuff in the material.
Right.
One part is all the fast dynamics. That's the stuff that's super sensitive to all those tiny details. It's the part that needs those really intense computational methods to get it right. And then you have the other part, the slow dynamics. That's less influenced by all those microscopic variations, so we can simulate it much more efficiently.
So we're talking about using different equations depending on if we're looking at the fast part or this slow part. How do you even start to split a problem like that? It seems really complicated.
It is. That's where this research really shines. They figured out how to split things intelligently. They used something called an implicit scheme for the fast dynamics and an explicit scheme for the slow dynamics.
Okay, hold on. Back up a sec. You're saying they use different schemes for each part, the fast and the slow.
Yeah.
What does that even mean, and how does that actually work when you're doing the math?
You're right. To focus on that, the different schemes are really important here. An implicit scheme, think of it like taking one of those super detailed photos.
Okay.
It captures everything, but it takes a lot of processing power to get it right. An explicit scheme, that's more like your everyday photo, faster, and it does the job when you don't need every little detail.
So it's like they're choosing the right camera for the job,
Mm-hmm.
using the fancy high-resolution one only where it really matters.
Exactly. Saves a lot of computational effort.
That's really clever. But how do they decide which camera to use? How do they figure out the split between fast and slow in the first place?
Okay, so this is where it gets even more interesting. They use something called eigenvalue problems.
Eigen what now?
Eigenvalue problems. I know, it sounds a little intimidating.
Yeah.
But the idea is it helps them find the natural breaking points.
In the data.
Yeah, the points where the dynamics are kind of like, okay, we want to be split up now, fast over here, slow over there.
So it's not random. They're using the math to figure out the most logical way to split it up. Like they're analyzing the flow and finding the best place to separate the highway from the scenic route, to use our earlier analogy.
Exactly. That's a great way to put it. And that's what's so elegant about this. It's not arbitrary. They're using the math of the system itself to make it as accurate and efficient as possible.
That's seriously cool. Okay, but let's zoom out for a second. We've got all this fancy math, these faster simulations, but why does it matter? What's the real-world impact of all of this? Why should we care about making this multi-scale math easier?
So the cool thing is this isn't just some theoretical exercise. It has huge potential to change things in the real world, like in material science or engineering.
Oh yeah, I'm listening.
Imagine being able to design stuff that's way lighter, but also stronger for like airplanes, or finding better ways to filter water or to get oil and gas out of the ground without messing things up.
So it's not just about making the math easier, it's about actually using it to solve problems.
Exactly. And what I love is that this is just the tip of the iceberg, this idea of splitting up complex systems, finding those eigenvalues, those natural breaking points, it could apply to all kinds of things.
Or like what? Give me an example.
Well, we've been talking about materials, but what about using it for like economic models or to understand how information spreads online, all sorts of things.
Whoa, that's a trip. It's so easy to get caught up in the details of the how, but thinking about the what-ifs, the bigger picture, that's what's really mind-blowing. We've gone from tiny pores to, like, the entire economy.
Right.
So, just to recap what we've learned today. So we took a deep dive, right, into this whole world of multi-scale flow problems.
Mm-hmm.
It's like those situations where the smallest things can have a huge impact on the big picture.
Yeah, and what I think is really neat is how this research just goes right at those problems. They're using the multicontinuum homogenization, simplifies things, and then they've got this splitting scheme.
Right.
That way they're not wasting computational power.
It's like they've given us this, like this mathematical toolbox we can use to solve problems that, I don't know, maybe we couldn't solve before.
Yeah.
We can figure out how things flow through all kinds of stuff. Porous rock, complicated materials, who knows what.
And like we were talking about earlier, it's not just about material science, right? This idea of finding those natural breaking points, like with those eigenvalues, it shows us the best way to split up a problem so it's actually manageable.
Right.
That's a powerful idea. It could apply to so many different fields.
So many possibilities. Like
Yeah.
we could extract energy more efficiently, develop better ways to deliver medicine, maybe even understand how society works better. This research is like opening a door to a whole new way of seeing things, you know?
Absolutely. And that's what I love about digging into stuff like this. We started with the really tiny stuff, those multi-continuum homogenization details, and now we're talking about like how this could change the future. It reminds me that even when math seems super abstract, it can have a huge impact on all of us.
I'm with you on that one.
Yeah.
Okay, so to wrap things up for our listeners out there, whether you're a math whiz or you just want to sound smart at your next coffee break, you now have the inside scoop on how mathematicians are tackling some of the toughest flow problems out there. But even more importantly, I think we've gotten a glimpse of how innovative thinking can lead to breakthroughs that have the potential to shape our world. And that's something worth thinking about no matter what your field is.